All right, this is probably a good time to start recording. Just get rid of these. All right, so I'm gonna start a little bit differently today. We're gonna be talking about calculus. So group theory, we did about 5 lessons, or 6 if you include 0. Um, so yeah, I'm gonna leave that for now. We can always go back to group theory. I'm gonna start on something that I think will maybe apply or will appeal to a wider audience. So hopefully to high school kids if they're interested in calculus, or undergraduate students or adults that are just interested in learning calculus. Maybe they never learned. So yeah, this is really just open to everybody. It will be pretty basic. I'll do a lot of problems. Of course, people can ask me more advanced questions, but I really want to make the videos more accessible to everyone. So this is lesson 6. Oh, and also we'll probably get into some multivariable stuff eventually, but I'm going to start out with the Stewart book. So I think this is like the Stony Brook edition, but you can probably just get a regular edition as well. And there's a very popular calculus book for college students, James Stewart. He's pretty famous. Well, when he was alive. All right, so we're going to call this lesson 6, an introduction to differential calculus. And I just wanted to start out with, what does calculus study? So what are the things that we're interested in learning? So lesson 6, intro to differential calculus. Right? And maybe if you've never studied it, or you've never, even heard about what the subject is about, you might be a little confused. Like, what does calculus actually study? So I wanted to write down a few things that we study in calculus. Right, so the most basic thing we study is functions between sets, but usually for calculus, you're talking about a function from the set of real numbers to the set of real numbers. But they could be multivariable real functions. So I'll just write functions in general. And if we want to be really specific, we would say like functions between sets, because a function always has a domain where the things are mapping from, and then a codomain where you're mapping whatever set you're mapping into. So we have functions, and then importantly, we have the limits of functions. And the limit of a function just means what value the function is approaching as we get closer to some value in the input. So I'll draw a picture in a little bit, but we have functions, limits, rates of change of functions. I'll just say rates of change. Rates of change, and then I wrote down a couple extra that might come up later, which is like the curvature of a function, or curvature of a line, or sorry, curvature of like a one-dimensional manifold, I guess you could say. There's a lot of different ways of expressing it. Or curvature, more generally, you could have the curvature of a surface or something like that. So maybe a little bit more advanced when you get into the multivariable stuff. There's more things you can do. Right, and then when you get into the kind of physics or the math that's sort of adjacent to physics, you can talk about velocity, acceleration. These are very calculus driven terms in physics. So velocity. And I'm probably going to spell this wrong, so if I spell it wrong, tell me in the comments. Acceleration. I feel like it's one L, but it doesn't look right with 2 L's. Or it doesn't look right with 2 L's, but I feel like it is 2 L's. I don't know. Acceleration. Not sure if this is one L or two L's. And then also optimization problems. So usually you'll have a function representing some value that you're either trying to maximize or minimize. And we want to go through what's the computation that you can do to find the derivative, right, which is how the function's changing, and also how to find then the minimum and maximum based on where the derivative is equal to 0. All right, so I'll just write optimization here. And when I say derivative, of course we haven't defined what a derivative yet is, but it will end up being the rate of change of a function at a certain point. So really, you could write in parentheses here like the derivative of a function. And also for velocity probably as well, like the velocity is the derivative of the position in physics, and actually acceleration is then the derivative of the velocity, right? So a lot of this, everything in differential calculus involves derivatives, right? Or at least limits, and then derivatives are defined by limits. But these are all kind of adjacent ideas, right? So let's, first topic in calculus, I'm going to so the plan is to kind of go through the topics, not to go through them too quickly, but just to do a lot of exercises. So I'm not going to like prove all the theorems or anything. I'm just going to kind of, state the main theorems and then show you exactly how you would use them to solve common problems, and really like the types of problems that will really illustrate what the math is doing. Or, the important aspects of the theorems without having to actually prove every single thing. So let's go into the limits of a function, and we're going to define what is a function. All right, so limits of functions. All right, so first let's define what is a function. I think they kind of give a vague definition in Stewart, so I'm going to give you like the precise set theory definition, although later they say this is the graph of a function, and essentially the graph of the function is the function. So we're just going to give a like strict set theory definition, which is if we have two sets, A and B, or really we could write A to B, which is specifying that A is the codomain and B is the, A is the domain and B is the codomain. So a function from A to B is really just a subset of A times B, which is the Cartesian product. So pairs of elements, which also you could call a relation, but it's a specific type of relation. It's a relation where there's only one output for every input, meaning that, so it's a subset, I'll write capital F, subset of A times B, and it's a particular type of relation between A and B such that for every little a in A, so for all A in A, for every element in the domain, there's a unique element which we'll call f of A, and A comma f of A is in big F. So there exists a unique element which we'll call f of A, little f of A, with the property that it's A comma f of A is in big F. Okay, so basically you're not missing any A's from here, so every A is given some output. Like there's no A's missing here, and for each A there's actually a unique f of A such that A comma f of A is in F. And sometimes you'll see this as the definition of the graph of a function, But I believe in set theory there is no like distinction between the two. This is really just this is the definition of a function between two sets. It's just a particular type of subset of A cross B. It has this property that for every A there's a unique f of A, and A comma f of A is in F. Okay, and then let's draw a picture here, right? There's this, the idea here is that there's this vertical line test, right? Because there is only one, there's a unique, when I write the exclamation mark here, that means there exists a unique f of A. So that means if you look at the graph of a function and you draw a vertical line, you'll see this taught in a lot of classes, that a function needs to pass the vertical line test in order to be a function. Meaning that if you draw a line through the graph, it should only intersect the graph at one point. So we'll draw the graph of a function and we'll show why it passes the vertical line test and why it actually is a function. Okay, so here A and B are both the real numbers, so we have a function, just the regular real number line. What is A times B now? The Cartesian product. It's the Cartesian product of the real numbers times the real numbers. This gives us a two-dimensional plane. So we'll say we're starting at 0 here, 1, 2, 3. And because it's the real numbers, we have all the numbers in between, right? All the fractions. And there's also like pi out here somewhere. So we have all the irrational numbers as well. 1, 2, so on. And so it's a function, right? Remember, we said it's a function if for every A in A, there is a unique f of A. Oh, I think I forgot to write this last time, but there's f of A is in B, of course, in the set B, such that A comma f of A is in big F, the subset which represents the graph of F. So that means that for every element here, if I pick an element like 1.5 or something, and I draw a vertical line up and down, this vertical line should only intersect the graph of the function at one point. If it intersects at more than one point, then this is not satisfied because there's not a unique f of A. There would be potentially more than one element. So you have the graph of the function will look something like this. And when it crosses any vertical line, it should only cross at a single point. Okay, so as long as we can assign for every value a unique value in the codomain, that's what a function is. But we have to do it for every single value. There needs to be some output for every single input, or else it's not a function, right? It might be a function on a restriction of the domain, but unless we're assigning an output for every single input, then it's not a function from the set A to B. Okay, so in this case, this curve that I just drew, you can see that it does pass the vertical line test. I could draw another vertical line here. It still only crosses at this one point here. If I draw one over here, it still only crosses at one point, right? Something that wouldn't pass the vertical line test, that would be like a circle, for instance. Like if you had another graph here and you drew a circle. A circle is a particular relation which is not a function, right? Because it doesn't pass the vertical line test. There's actually 2 points for every vertical line except for the vertical lines that are like tangent on the left or right. Right, so we have relations, particular relations that are functions. We have relations that are not functions, like this circle. And yeah, and then so for limits of the function, we want to talk about what value is the function approaching as you get closer to one of these vertical lines, for instance. So as you get close from the left, if you approach one of these vertical lines from the left, you'll be approaching some value. If you approach it from the right, you'll be approaching some value. But that's not always true for every function. The function I drew here happens to be a continuous function, so all of its limits exist at every point, but that won't always be the case. Okay, so this is, a visual picture. What is a function? It's it's some relation which has a graph that passes the vertical line test and has an output for every input. That's a function. And usually, like I said, we'll be dealing with functions from the real numbers to the real numbers, and there's a reason for that, and that's because this is the set where all the limits actually exist. So there's a little bit of problems with limits if you don't include all of the real numbers on the number line. If you just include like fractions and rational numbers only, you can you can miss out on some limits. There can be limits of functions that are kind of missing in some sense, where the value is missing in the limit. Okay, so limits of a function. We just drew some functions, so now let's talk about what is the limit. I'll write down the strict definition, but usually we won't actually use this. So I just want to write this down because I think it's important that everybody studying calculus, you actually see this. You've probably seen this if you're taking a class, but if you're not taking a class, then you probably haven't seen it. So limit of f of x. So f of x is a function, right? X represents the input, and f of x is the output. So limit of f of x as x approaches a, and usually we'll write as x arrows to a, or x approaches a from just x approaches a. It could be from the left or from the right if we don't specify. And usually we'll write this as limit as x goes to a of f of x, and then if this limit exists, we'll say it's equal to L. And the definition of this, so the fact that this limit exists is only if this definition holds. So I'm about to write down the definition. So the definition of this is if there exists a number L, which is a real number, so if there is some number L with the property that for every epsilon greater than 0, so for every number, you can think of it as a small number. For any small number greater than 0, it could be 0.01, it could be 0.001, 0.0001, right? Just keep getting closer and closer. It needs to be true for every epsilon. No matter which epsilon I pick, there should exist a delta, which is also greater than 0. Such that if I get this close, if the x value gets delta close to x, I should be at least epsilon close to L in the output of the function. So this limit exists and it's equal to L if there exists a number L with the property that for every number epsilon greater than 0, there exists some other number which might depend on epsilon, delta, which is greater than 0, such that if the absolute value of x minus a is less than epsilon, then that always implies, if I'm closer than epsilon distance, or sorry, actually this is delta. Delta is for the domain. So if I'm delta close to a from the x variable, so if x is really close to a, then I'm always within epsilon distance of L for the output, which means that the absolute value of f of x minus L is less than epsilon. Okay, and then very important definition here. I just want to look at the board and make sure it's easy to see. Okay. And I just want to restate this definition again, like I said, because this is one of the most important definitions in all of calculus. So it's saying that the limit of the function exists and it's equal to L if there exists a number L with the property that no matter which number I pick that's greater than 0, so no matter how small I make epsilon, there is always some small number delta, such that if x is really close to a, it's delta close to a. It's within delta distance of a in absolute value. So if this is true for some x, then it's also true necessarily that f of x minus L is within epsilon distance. So f of x minus L in absolute value is less than epsilon. So in one more final generalized way of saying it, if I'm delta close to a, then I'm always epsilon close to L in the output for f of x. All right. Not sure if anybody's watching, but are there any questions here? I think this would be definitely a good time to ask questions. All right. And then there's a definition. I'm just gonna kind of write it down. It's a little bit like skipping ahead, but I think it's important to write it here. I just want to state what it means for a function to be continuous. So this is the definition for the limit to exist at L, and then we have a notion of a continuous function, which is a function where the limit of the function at a certain number is actually just the function value itself. So when L is just f of a here, then we call the function continuous. And maybe I'll draw a picture here too, just to illustrate what the notion of a limit is trying to convey here with this technical jargon with this epsilon and delta notation. So everybody that studied this has seen the epsilon delta definition, but most people, unless you take like the real analysis class, you don't ever really use it. But I think understanding the definition is still very important. And so here I'm just going to write another definition. So if the limit as x goes to a of f of x equals f of a for every a in whatever domain you're working in, usually it's the all real numbers. We'll just say all real numbers for now. So if the limit of the function at a is just equal to f of a, then we say it's continuous at, we say it's continuous at a, but if it's continuous at every point, then we just say it's continuous. So if it's true for every a, then we say f is continuous. Or if it's just true for one particular a, then we say it's continuous, f is continuous at that a. But the picture here, the notion, or the visual notion here is that you have some function here from the real numbers to the real numbers, and if I pick a particular point, any point, and I look at the limit of the function as I approach that point, it's actually just approaching to the value of the function. It's not true that, for a discontinuous function or a function that is not continuous, the limits they might not exist. So when you approach the function from the left or from the right, you might not be approaching the same value. You might not be approaching any value at all, or you could be approaching different values. There could be some sort of jump discontinuity at the point or something, right? But if the limit exists at every point and it's equal to the value of the function at that point, then we just say it's a continuous function. Okay, and then we have some examples of continuous functions, like all polynomials we can prove are continuous. Absolute value function is continuous at every point, including 0. Also, we can prove that if we compose two continuous functions, remember in group theory we said we could compose functions and get a new bijection. Here, if we have two continuous functions, we can compose them and we get another continuous function. We can actually show that the definition I just erased, if we have two functions that satisfy that and we compose them, you can show that that new function also satisfies the same conditions. Right, so polynomials, absolute value of functions, compositions of functions. There's basically a lot of continuous functions. Any analytic function, any Taylor series, if you guys have heard of those terms. If it's convergent Taylor series, it's continuous. And in fact, it'll be smooth and infinitely differentiable as well. But we're not there yet. Right, and then a couple non-examples which are kind of interesting for functions that are not continuous. I'll write non-examples. Oops. Two interesting ones are, first you have a step function. So it's the function that's defined. Well, there's a couple different ways to define it, but maybe we could say it's 0 if x is strictly less than 0, and it's equal to 1 if x is greater than or equal to 0. This function is not continuous at 0 because the limit at 0 from the left of the function is 0, and the limit from the right of the function is 1, and therefore the limit doesn't even exist at 0. But if it did exist, it would have to be equal to 1. And we see the limit from the left is 0, so it can't be equal to 1. And then another interesting one, which is a little bit of the same idea, but a little bit more complicated, which is the function is 0 if the number is a real number, or sorry, if the number is a rational number. Or actually, let's do it the other way. If x is not a rational number, then it's 0, and it's 1 if x is a rational number. Meaning that, like, if I plug in f of pi is not rational, so I would get 0. But if I plug in like f of 1/2 is a rational number, it's a fraction, therefore I would get 1. And this is called the indicator function for the rational numbers. It just spits out 1 or 0 based on whether the value is in the rational numbers or not. So it's it indicates that it is a member if it's 1, and it indicates that it's not a member if it's 0. So both of these are discontinuous functions. In fact, the second function is actually not continuous at any point. So it's actually kind of hard to draw this function because there would be countably infinitely many points that are dense where the value is 1, and then there would be infinitely many uncountably many infinite points that are also dense that are interspersed amongst the ones that are equal to 0. So there's actually more zeros than ones, but they're both infinite, and they're both dense in the real numbers, so they take up, in some sense, like all the space. And yeah. Yeah, well, not take up all the space, but they're sort of found at every point, or at least close to every point. Okay. So two examples of functions that are not continuous. The first function is not continuous at 0, but is continuous at every other point. And the second function is actually discontinuous at 0 and discontinuous also at every other point as well. It's actually, there's no point where this function is continuous. And the reason is that no matter which rational point we're at, we're also near an irrational point. So there's, like I was saying before, there's a lot of zeros that are really, really, really close to ones. And it doesn't matter how close we get to a particular rational number, there's still irrational numbers near it where the value is not equal to 1. So, yep. So if you just need some examples or you want to go through more carefully in your own time, like thinking about why these two functions are not continuous, I think that's definitely a good exercise that will help you understand this notion of continuous versus not continuous. At a particular point versus at some other point. It might be continuous at one point, not continuous at another, for example. Okay, and then let's just do some examples of limits. So if the function is continuous, then usually the limit is very easy. You can just plug in the value of the function. But you have to be sure that the function is continuous, that it's actually defined there, and that you can just plug in the value. So there's a lot of functions that are sort of not fully defined on all real numbers. For example, this one we'll do right now. Right, and when I said that a function is usually from the real numbers to the real numbers, you can also define a function on a subset of the real numbers to the real numbers. So we might leave out some points, like for instance, square roots. There's no square root of a negative number, so whenever you see it like square root of x, the domain is going to naturally be the non-negative numbers, so it won't include all real numbers, but that's not usually an issue. Usually the domain is pretty well behaved. It's usually some nice subset, like just the positive numbers or just the negative numbers or something like that. So yeah, these are problems from Stewart, from the Stewart book. This is number 9. It just says evaluate the limit if it exists. And that's what we shall do. So the first one, number 9, that I picked to go over, says, what is the limit as x approaches 5 of x squared minus 6x plus 5 divided by x minus 5? And the key here for this problem is, first you need to notice that this function is not actually defined at x equals 5. So if we want to use the theorem where, okay, well, it's a continuous function, we can just plug in the value. Here it doesn't work. If we try to plug in the value here, we get 5 squared minus 30 plus 5 is 0, divided by 5 minus 5 is 0, so we actually get 0 divided by 0. That's not a number. But usually in calculus, when you get a 0 divided by 0 answer, when you plug in the value and you're trying to do a limit, usually that just means you're going to have to either do some algebra, or later we'll actually have something that helps us, which is called L'Hopital's rule, which will make this problem even easier. But here, let's solve this without that. So usually the way to approach these problems, these rational functions, is you're going to want to factor the top and bottom. And in this case, you'll see that one of the factors on the top actually is x minus 5, and that will cancel for all the numbers where we can actually plug in an x, which is of course not x equals to 5, but we could plug in numbers really, really close to 5. So let's factor this fraction. And if you remember your factoring, if you ever learned it, maybe you didn't. Of course, if you didn't, then you can always ask me for help. But you're going to be looking at the coefficients, and you're going to use that information to try to determine the factors. So for here, we're basically looking for two numbers that multiply to equal 5 and that add up to equal negative 6. Well, that's clearly just x minus 1, x minus 5, because minus 1 times minus 5 is positive 5, and minus 1 plus minus 5 is negative 6, and 1 times 1 is 1. So that's how you factor that one. Or there's, of course, you have your long multiplication for polynomials, which is sort of annoying, but for these small degree ones, it's not too bad. Right, and like you can see here, we have this x minus 5 term on the bottom, x minus 5 on the top. We can cancel those, and now it's saying basically for every value of the function where we can actually plug in an x, this function is just equal to x minus 1, which means that there's just sort of a removable discontinuity at this point. That basically we could plug in the value of x minus 1 at this point, and it would allow the function to be continuous. So there's in some sense there's like a hole missing in this x minus 1 line. So it looks like the graph looks something like this, right? At x minus 1, but at x equals 5 there's some sort of hole missing here. But just because the hole's missing, that doesn't mean if we approach this value we're not still just approaching 5 minus 1 here. So when we look at the limit here, we can, once we reduce it to a continuous function at every point in some close distance to the point that we're finding the limit of, then if it's continuous, then we know which value it's approaching when it goes to 5, because x minus 1 is continuous. It's just approaching the value of the function at that point, which is just 5 minus 1, which is just 4. Right, so this is saying that even though we can't plug in 5 into the original function up top here, this rational function at the very beginning, we can't plug in 5 because we get 0 over 0. If I plug in 4.99999999999, I should get something that's very, very, very close to 4. I should get like 3.99998, whatever, right? I hope I said that in the right way. But yeah, basically you can't plug in 5 in here, but if you plug in numbers that are really, really close to 5, you'll get something that's really, really close to 4. So that's what this is saying here. The limit of this function, even though the value of the function doesn't actually exist when we plug in x equals 5, when I plug in things that are close to x equals 5, I get things that are close to y equals 4, or f of x equals 4. Okay. Let's see. Okay, so I'll do another one similar to this, number 19 in the Stewart book. All right, so same type of problem, just evaluate the limit if it exists. Limit as x goes to -4 this time, and the top of the fraction is 1/4 plus 1 over x. And then we take that and we're going to divide by 4 plus x. And then again, you'll notice that if you plug in -4 on the top, you get 1/4 minus 1/4, which is 0. And if you plug in -4 on the bottom, you get 4 plus -4, which is 0. Again, we have 0 over 0. So similar type of problem. 0 over 0 means the limit might exist. It might not exist, but we have to do some sort of simplification here. If we're not using L'Hopital's rule, which we'll talk about later, not later today, but maybe in the next couple lessons. If we're not using L'Hopital's rule, then we need to do some sort of algebraic manipulation until we can reduce this either to some continuous function, thus we find the limit by just plugging in the value of the continuous function, or we show that it reduces to some sort of like infinite blow-up where there is no limit, or the limit on the left and right, maybe they're not equal, right? So here, one way to do this is instead of having like a sum of fractions, it's a lot easier to write it in the form that we had for the first problem, where it's just a rational function divided, a rational polynomial. So one polynomial divided by another. Here, it's not a polynomial because 1 over x is not a power of x. It's like an inverse power of x. So we have to do a little bit of work here to rewrite this as a rational function, but to do that we need to rewrite the top as a rational function, and that's just a we want a common denominator, so we're going to multiply like the top and bottom of the first fraction by x over x, and the second fraction by 4 over 4, thus not changing the fractions, but we get something like x over 4x plus 4x over 4x all over 4 plus x. And now, because these are the same denominator, I can actually just add these on the top and divide it by the common denominator. So we can just rewrite this with just a single 4x. And what was it again? Oops. 4, I don't know, it was x. Oops. X plus 4 over 4x, and then we're dividing this whole thing by 4 plus x. And if you remember your fractions, your fraction math, right, when you have a divided by b and then you divide that whole thing by c, that's the same thing as a divided by b times c. So I can actually just take this denominator here and multiply it on the bottom, and we get the same thing. I'll rewrite that. So really this is just x plus 4 divided by 4x times 4 plus x. And then again, just like the other problem, the x plus 4's cancel. Well, 4 plus x is the same thing as x plus 4. And now we have 1 over 4x, and that is a continuous function at the values that it's defined at. Not at 0, unfortunately, but we're not taking the limit at 0. So if I just plug in the value here, this is just 1 over 4 times negative 4, so we get negative 1/16. So again, the function is not defined at negative 4, but if we plug in values that are really close to negative 4, like negative 3.99999, the output of the function should be really close to negative 1/16. And you can actually check this on a calculator. If you don't believe me, you can take out your calculator and start plugging in 1/4 plus 1 over 3.999, or negative 3.999, and then plug in 4 plus negative 3.999 and see how close you can get it to negative 1/16. All right, so I had 2 more problems, but I think I'm going to skip one of them. One of them talks about the squeeze theorem. I think it's just going to take up a little bit too much time, so I'll probably do the squeeze theorem next Tuesday. And I'll just do this other problem to finish up. So this is number 38. Oh, I didn't say which section this is, I'm sorry. So these are actually the original problem as well in the Stewart book. This is section 2.2 is the limit of a function. But I don't think that's where I got it. No. Yeah, so 2.3 is calculating limits using limit laws. And that's where I got that number 9 problem and number 19 from. So that's on page 111, 111. That's where you'll find those 2 problems that I just did. And now problem number 38 is on the next page. At least this is the Stony Brook edition, so it might be different numbering and you might have different problems. But either way, you can still follow along with what I'm doing on the board. This is number 38. Number 38, Stewart, page 112. The single variable calculus book. And here he now defines a new function, which is the ratio of 2 continuous functions. So it's x squared minus 1 divided by x minus 1 in absolute value. And the trick here is that although these 2 functions are actually both continuous, when you take the ratio of the 2, it's only continuous where the bottom is not equal to 0. So it is true that if you take 2 continuous functions and you divide them, you get a continuous function. But you have to be sure that the bottom function is never equal to 0 for that to be true. If the bottom function is equal to 0 sometimes, like when x equals 1 for instance, then your function might not be continuous there. So the first problem, part I says what's the limit as x approaches 1 from the positive direction? The second part says what is the limit as x approaches 1 from the negative direction? So this little negative sign here and the little positive sign next to the 1 in the limit, next to the arrow, that tells us which direction. So positive means we're plugging in numbers that are bigger than 1, and we're seeing as we get closer to 1 from the positive direction, is that approaching something? And negative direction is the same way, just the other direction. And the key here is that this function here the bottom is defined as just x minus 1 when we're plugging in numbers greater than 1, because that's how the absolute value is defined. Right? The absolute value is when the number is greater than 0 that we're plugging into the absolute value, you just get the same number back, right? So if I plug in like 1.00001 here, I'm just going to get 1.0001 minus 1. Absolute value of that is just itself. So when I'm approaching from the positive direction, the bottom is just equal to x minus 1. So I really just have x squared minus 1 divided by x minus 1, and I can ignore the absolute value signs here. So this is, and x squared minus 1, that factors as x minus 1, x plus 1. So really this is just, I'm just left with x plus 1 after the x minus 1's cancel. X plus 1, when I plug in 1, I get 2. So it's like 1 plus 1, 2. But when I approach 1 from the negative direction, then this absolute value sign actually flips the number. Because when I plug in numbers less than 1, I'm going to be getting something that's negative here. When I take the absolute value, I'm going to get the negative of the negative number, and it's going to become positive again. So really, this is like now x minus 1 times x plus 1 divided by negative x minus 1. So now it's basically the same fraction, but I pick up a negative sign. So this is negative 1 plus 1, which is negative 2. And now it's maybe obvious, maybe not so obvious, but if the limit from one direction is equal to one number and the limit from the other direction is equal to a different number, then that means that the limit doesn't exist, because no matter which way I approach that particular number, it should be going to a single value, which was that L that we had in the definition. But L can't be simultaneously equal to 2 and negative 2 at the same time. Therefore, any number that has a left limit and a right limit that are not equal to each other, that means the limit can't exist. And that's the part B. Part B asks, does the limit as x approach 1 of f of x exist? And then we say it doesn't exist, because if it existed, then the left limit and the right limit would be equal. But here they're not equal, so limit as x approaches 1, sometimes we'll write like does not exist. So limit of f of x as x goes to 1 does not exist, because the right limit and the left limit are not equal to each other. And then the last part of the problem says sketch the graph of f. So let's just look at what type of function is x squared minus 1 divided by the absolute value of x minus 1. Well, let's see. So we had f of x equals x squared minus 1 over absolute value x minus 1. So if x is greater than 1, then f of x, well, if x is greater than 1, we said that the bottom was just x minus 1, and then the factor of x minus 1 on the top cancels, so it's just x plus 1. And if x is less than 1, then it's the same fraction, but the bottom becomes negative, right? So it's basically the same thing, but it's the negative of this, so it's minus x minus 1. Right, which is just x plus 1 divided by negative 1, because then the x minus 1 terms cancel. And so if we graphed this, it would look, well, I didn't leave myself much room, but so it'll be x plus 1 for all numbers greater than 1. X plus 1, so something like that. And then it's minus x minus 1. It's going to go this way. Yeah. Right. So basically, you get these two lines, but you have this discontinuity where when you approach from the left side, you're getting closer and closer to -2. When you approach from the right side, you're getting closer and closer to 2. And the function's actually not defined at x equals 1. You have this discontinuity because you're dividing by 0, basically. So you have a problem. Okay. Right. I think that's basically all I wanted to cover. Like I said, I had a problem about the squeeze theorem. So if you haven't heard of the squeeze theorem, that's okay. But basically, it's a theorem that allows us to prove certain limits where it's not so easy to do it like algebraically. You're basically comparing a function that you don't know the limit of, and you're squeezing it between two functions that you do know the limit of, and you can prove that the function in between them also approaches the same limit. So I'll do that probably next time. Is there any questions? All right. So that was our first calculus lesson, and I'll keep going with calculus for probably at least like 5 or 6 lessons here. I might go even further than that, depending on how many people we get in here, how much interest there's shown into it. But yeah, hopefully this has been fun. It's been fun for me, and I hope you guys enjoyed learning calculus. All right, I'll stop it here.